First, we're gonna start with some problems that we see every day, and it's occurring in our world. First, the power grid does not reach everyone everywhere. That means there is an isolated homes that have no electricity supply. Second, if you're gonna choose a solution for that, it would be renewables like solar panels and wind power. But renewables are not available all over the year. Like in the night, there is no sun, and the wind, it's like season. We will find it in season of the wind. It's not available all over the year. So if you're gonna choose a solution beside the renewables, it's gonna be hydrogen. Hydrogen, it's very have a dense power. But hydrogen, it's never found pure in nature. It's highly reactive, and you never found hydrogen pure alone in nature. Second, if we're gonna choose the hydrogen that is produced today by manufacturing, we're gonna use the hydrogen that is produced by fossil fuels, and these fossil fuels are causing so much severe harm to our planet Earth. The problem that we have created is that there is to solve it. What are the technical challenges associated with the practical implementation of PV hydrogen system, and how can they be addressed to ensure its viability in isolated regions? We suggest this work plan so we can better solve the problems that we mentioned. First, we're going to go through an overview of electricity production system based on hydrogen. Second, it's the mathematical modeling of the PV hydrogen system. Third, it's the simulation of our system. And lastly, we did a small prototype and the concept of practice, and we calculated the cost analysis of the whole system. Main objectives we're gonna focus on in this presentation. First is to simulate a fully functional system. Second is to generate sufficient power to supply an isolated site. And the third is that the hydrogen power is greater than sun power. Like if the sun is generating 800 watt, the hydrogen must be greater, like 6 kilo or so. Introduction. Green hydrogen is a clean energy carrier. It's not an energy source, it's an energy carrier. And fossil fuels, it can be produced from renewable source like solar energy through electrolysis. Electrolysis then used in fuel cells to generate electricity with water. The only byproduct, like there is no CO2 emissions, there is no harm to the environment, there is only water as a byproduct. First, here we have some properties of hydrogen as a molecule. Hydrogen is the lightest element in the periodic table, and here is the mass number, its number of electrons. We focus on this table, we focus on one or two things, like freezing point is so much low, and the hydrogen is highly flammable gas, and if you're gonna produce electrical energy by hydrogen, you're gonna need 1 kilogram to generate 33.3 kilowatt hour. First, the hydrogen production today is classified by a rainbow. This rainbow consists of many colors, but we're going to focus on only 4 colors. First, we have brown and gray. Brown and the gray colors are CO2 emissions. Like here we see that gray is so much, it's a lot of like 41–42%, it's a lot, and gold is the majority of this graph. But when we say blue it's the same as gray and brown, but with capturing CO2, like there is smart technologies that we can capture CO2. Lastly, we have green hydrogen that our system is based on. We are using electrolysis. The electrolysis is like we need electrical energy. These are the anode and the cathode. Inside here there is the membrane. It's white membrane. The water gets inside and get split into, like you see here, oxygen and you see hydrogen. The membrane is don't let oxygen to pass through, so the hydrogen is going through and the oxygen is, so the water split is successful and the electrons have a closed path. There is the closed path from the anode to cathode. The electrons from the water goes through the cathode and complete the circuit. Second, if we're gonna use hydrogen, we must have a hydrogen storage. First, we have hydrogen as a compressed gas. We're gonna use compressed gas like 350 and 700 bars in tanks to store this hydrogen. And we need liquid hydrogen, as we talked about. It's highly low, minus 259. It's highly low, but if we're gonna use liquid hydrogen, it's good, and we eliminate the high flammability of hydrogen. Lastly, we have the solid state. Like we can store hydrogen in solids like metal. But it's not highly used. There is types of fuel cells. First, we have the proton exchange membrane fuel cell, and we have a solid oxide fuel cell. Lastly, we have alkali fuel cell. This shows of the fuel cell. Like the fuel cell, it's the exact, it's the opposite of what we talked about, the electrolysis. We have here hydrogen is going through this side here, and the oxygen is going through this side here. As hydrogen ionized, this solid membrane is gonna let hydrogen through this solid membrane. This hydrogen is gonna meet up with oxygen. As we can see in the top, electrons that doesn't let through by polymer, pass through this fan and we're going to generate electricity. And as electrons pass through, we're going to have water as only a byproduct. Now we're going to move on to the modeling of the system, like the mathematical modeling. First we have the power of the solar panel. Second, we have the voltage of the electrolyzer. It's the voltage here we can use only like ideal, but we managed to go through the ideals, and we use losses like activation losses, ohmium losses. This is the open circuit. The voltage of the fuel cell, it's like the inverse of the electrolysis. Like we have plus here, we have minus here. The results of the photovoltaic in the mathematical modeling. First, we have our power by voltage. We see here that when the solar radiance is going up, we have that the power is going up. Like here it is the maximum power point that we focused on in our MPPT algorithm. We see the same for the current. Like the current by voltage, the current is also related to the sun irradiance. The results for our electrolyzer, like we see here, there is a sharp going up. This region is called activation loss. Like in the first of the reaction, the electrolyzer is sucking a lot of energy. Like there is a sharp high up, and then the system is linearized and it's stable. And we have this graph shows the humidity of the electrolyzer. Like this is the current in function of the water saturation. If when the water saturation is going up, the current is going up. Like this is understood. When the water is when we have a lot of water, we have the system will suck a lot of energy, and this is why electrons are high. Next, we have the results of our fuel cell. Like in the previous, we have here the activation loss, then the system is generalized and stable. This is the distribution of water inside our fuel cell. Here we can see that the water is high in the region where the water is created, and it's low when the hydrogen is going going inside the fuel cell. Another result, we have the power of the fuel cell. We see it's going up slowly. And second, we have the temperature effect on the fuel cell. Like we see here, this is the values of the temperature we used to generate this graph. Like you can see, the temperature have so many effects on the fuel cell.